This is our next topic under BJT amplifiers, the BJT modeling. Capacitors serves two primary roles in transistor amplifiers. Coupling capacitors pass an AC signal from one device to another while providing DC isolation between the two. The other one is a bypass capacitors are used to short circuit AC signal to ground while not affecting the DC operation of a circuits. So these bypass capacitors are usually used at the emitter stabilized bias amplifier. Remember, in your emitter stabilized amplifier, you need your amplifier to be stabilized so that it can generate an output at your collector which is stable even though it is cut off or it is in saturation. In most practical application, you will not see a single transistor amplifier. Rather, there will be a series of cascaded amplifiers. The term cascaded means connected in series. So in this figure, we have two amplifiers connected together. Stage 1, then it followed by a stage 2. And if we call this one as your multi-stage amplifier. Stage 1 is connected to stage 2 with a capacitor, that is C2. So C2 is what you call your coupling capacitor. Bypass capacitors perform functionally in the same manner as coupling capacitors, but they are used for a different reason. Bypass capacitors are connected across the emitter resistor of an amplifier to keep the resistor from affecting the DC operation of the circuit. As we can see that your amplifier is only those circuits after your C1 and before your C2. So resistor RS is not part of your amplifier and resistor RL is not part of your amplifier. So because RS is part of your input elements and your RL is part of your load element. So CE is what you call your bypass capacitor. At this point, we need to derive the EC equivalent circuit for a common emitter amplifier, which is used in many EC calculation. It is easily derived using these two steps. First, you have to short circuit all capacitor. Then second, you have to replace all DC sources with ground symbol. So the basis of this first is easy to understand. Since the capacitor acts as a short circuit to the AC signal, and the second step is based on the fact that DC sources have extremely low AC resistance values. So the internal resistance of a DC source is ideally 0. So we have to rewrite your circuits into this manner that all your ground is connected on the level of all ground symbol. So we have R1, which is now in parallel with R2, and your RC, it is now in parallel with RL. And remember that your amplifier is the component from R1 up to RC. Then we have to get this R1 since it is in parallel with R2, as we have to call this one as RB. But we cannot do the same operation as we have with your RB with RC and RL because RL is not part of your amplifier circuit. So we have now your simplified model where RB is equivalent to your R1 in parallel with R2. So we have this current IS. Then we have your IB, this will be your IO, IC, and your IE. The primary function of a model is to predict the behavior of a device in a particular region. At DC, the bipolar junction transistor works in either cutoff or saturation. In EC domain, operation of this type of this transistor is quite different, and this transistor works in the linear operating region. So we have now to change your transistor into an EC equivalent model. And there are three models. The first one is the RA model. The second one is the hybrid model. Under hybrid model, we have the approximate hybrid model and complete hybrid model. And the third one is the hybrid pi model. So RA model reflects the operation of the BJT at mid frequencies and is sufficiently accurate. The RA model is an equivalent circuit that can be used to predict performance. Then, what are these important parameters if we are solving EC equivalent circuits? So we have the input impedance, which is equivalent to B over I. So if you have input impedance I, that is equivalent to BI over I input. Output impedance, the output impedance is determined at the output terminals, looking back to the system with the applied signal set to 0. Voltage gain, that is your output voltage over your input voltage. Current gain, that is your output current over your input current. And the power gain, that is your power output over your power input. So we begin with our RA model in the common base configuration. So this is our configuration for a common base, where the base is common between your input and your output. Your input is the emitter and your output is at the collector. So we have this current at your input as your IE. Then at your output, that will be your IC. Then we have IB going to the ground. So we have to change this transistor into an EC-RE model. So this is the equivalent of your EC-RE model. So we have your emitter, which is represented by an arrow. So this one, we have an arrow to determine that is an emitter. It is equivalent to a diode. Then we have your current IC that is going from your transistor. So we have IC here that is also going up, going to your collector terminal. And we have your internal resistance, or we call this one as RO, that is a resistance between your collector to emitter junction. And we have your BO, that is across your collector with respect to base, and your B input, that is from your emitter with respect to base. And this is your IO, which is in opposite direction with your IC. And also your IO is also in opposite polarity with your voltage BO. So this is positive for our BO and this is negative for our BO. Then your IO is in reverse polarity with your BO. So this is our input impedance. So if we have to get your internal resistance RE, as you can recall in our PN junction, that REC is equivalent to a 26 millivolts over IE. Your output impedance is at your output terminal. Then your IC is equivalent to your alpha IA. Remember, if we have the ratio between your output over input. If your input is your emitter and your output is collector, we call that one as alpha. So we have a current ratio of IC over IE, which is equivalent to alpha. So solving for your IC, that is equals to your alpha IE. And this RO, it is optional. So we have to solve for your input impedance. So remember your input impedance, that is BI over I input. Your BI is equivalent to the voltage across your RE. The current that flow in your RE is your IE. And your I input is the same as your IE. So substitute dividing your equation BI with II, so therefore your input impedance is equivalent to RE. Then for your output impedance, we have to set the input signal to 0. So therefore your I input, which is equivalent to your IE, is equals to 0. If IE is 0, so therefore IC is also 0, resulting into an open circuit. So therefore output impedance is equivalent to RO. For the voltage gain, that is BO over BI, where your BI is equivalent to REIE and your BO is equivalent to your negative ROIO. But remember, your IO is in opposite direction with your IC. So we have IO equals to negative IC, and remember IC is equals to alpha IE. So we have IO equals to negative alpha IE. Substituting that one to your voltage gain, so therefore we have your voltage gain equals to your BO, which is RO alpha IE over your BI, which is RE IE. Or therefore, your voltage gain is equivalent to your RO alpha over RE. For the current gain, we have IO over I input, where I input equals to IE, and your IO is equals to your negative alpha IE. So therefore, your current input is equals to negative alpha. For the common base configuration, but before that one, we have to get your output impedance if your RO is optional or without RO. So if it is without RO, your common base configuration output impedance is equals to infinity. Then we have the common emitter configuration. This is your common emitter. Your input is now at the base and your outputs the same at the collector, with your emitter as common between your input and output. So we have this current I input, it is equivalent to IB, and we have your current IC and your IE. So we have to change this one into an RE model. So since we have this emitter, so we have to represent your emitter with a diode. So this is your IB, IC, IC and IO has the same direction. Then we have your IE. Voltage input that is from the terminal of the base with respect to your emitter, and your voltage output that is from the terminal of your collector with respect to emitter. Then your IC is equivalent to beta IB, and your IE is IB plus IC. And since IC is beta IB, so therefore we can write IE is equivalent to quantity beta plus 1 IB. So for your voltage input, that is equivalent to your BE. So if we have to solve for your input impedance, which is BI over II, so that is equivalent now to BE over II. But what is BE? BE is equals to RE times IE. And if we have to substitute IE with your voltage input, which is equivalent to your IB, so therefore we have BE equals to RE beta plus 1 IB. Dividing this equation by its current, then we can have your resistance. And we call that one as your input impedance. So therefore, input impedance is Re times beta plus 1. Or we can approximate your input impedance as beta Re. So if we have to redraw the circuits using this input impedance with this beta Re, so this is now your equivalent model. So we have your beta Re at the input side, and we have your BO in that is across your RO, and we have your IC. So this is IB, IC, IO, input impedance, and output impedance. So if we have to solve for your input impedance, it is BI over II, where BI is equivalent to beta REIB, and your I input is equivalent to IB. So therefore, input impedance is equals to beta RE. For the output impedance, since we have to set the signal of your inputs into 0, so therefore I input, which is equivalent to IB, is 0, and IC is also 0. So we have output impedance equivalent to RO. For the voltage gain, which is BO over BI, where your BI is equivalent to beta REIB, and BO is equals to negative ROIO, and IO is equals to IC, and IC is equals to beta IB. So therefore, BO is equals to negative RO beta IB. Substituting that one to your equation voltage gain, so we have negative RO beta over beta RE. So IB and IB is cancelled out. So we have only negative RO over RE. Then for the current gain, which is equivalent to IO over I input is your IB, and your IO is your IC, which is equivalent to beta IB. So therefore, current gain is equivalent to your beta. Without an RO, your output impedance will be infinity. For the hybrid equivalent model, since RE model for a transistor is sensitive to the DC level of operation of the amplifier, the result is an input resistance that will vary with the DC operating point. For the hybrid equivalent model, the parameters are defined at the operating point that may or may not reflect the actual operating condition of the amplifier. This is due to the fact that specification sheets cannot provide parameters for an equivalent circuit at every possible operating point. They must choose operating conditions that they believe reflect the general characteristic of the device. So if we see if it is what is the most sensitive method of solving amplifiers between hybrid and RA model, it is the RA model because it reflects the actual operation of your transistor. Whereas for the hybrid, your parameters was only given by the manufacturers, and this type of parameters does not reflect the actual operating condition of the amplifier. Hybrid model is represented in a two-port network. One port is a Thevenin's equivalent circuit, and the other is a Norton equivalent circuit. So we have this one as a Thevenin's equivalent circuit, and this is your Norton equivalent circuit. So for your Thevenin's, we have H11, H12, B2 with BI. For your Norton, we have H21 and I1 and H22. We have B2 at the source voltage of your Norton, and we call the current at your Norton as I2 and the current at your Thevenin's as I1. If you have to get the equation of your port 1, which is the Thevenin's equivalence circuits, so that is equivalent to BI H11 I1 plus H12 B2. For your Norton, remember Norton, it is a current-based circuit. So we have I2, which is equivalent to your H21 I1 plus H22 B2. So if we have to set B2 to 0. So we can solve for your H11 as equivalent to your B1 over I1. So B over I, that is equivalent to a resistance. So we have a unit of ohms. And if we have to set I1 to 0, then we can solve H12, which is equals to B1 over B2. So we have voltage over voltage, that is unitless. On the other side, if we have to set B2 to 0, then we can solve H21, which is I2 over I1. The same current over current, that is unitless. And if we have to set I1 to 0, then we have I2 over B2. So since B over I is equivalent to resistance or ohms, and this is an opposite, so this is what you call your Siemens. So we have to call your H11 as HI, or that is input resistance, and your H12 as HR, or that is reverse transfer ratio. Why it is reversed? Because your input voltage is B1 and your output voltage is B2. So we have input over output. So we have what you call your HR reverse transfer ratio. Then for your H21, we call this one as HF. It is equivalent to your forward transfer ratio because we have I2 over I1, where I2 is your output and your I1 is your input. And H22 as HO, or we call that one as output conductance. So for a common base configuration, the equivalent EC model in hybrid pi will be this one. So we have HIB, HRB, BC, because why it is BC? Because your opposite voltage is B with respect to, or C with respect to B. Then we have HFB, IE, because your input current is IE. And we have HOB. For your current common emitter configuration, so this is your equivalent hybrid model. We have IB, HIE, HRE, BC. Then we have HFE, IB. IB is your input voltage or input current. We have IC, then HOE. So this equivalent hybrid model, even though it is a common base or a common emitter, they have the same circuit configuration. Only the subscript that will determine what type of configuration that you have. If it is common base, then you have a subscript of B. If it is common emitter, then you have a subscript of E. So we call this one as a complete hybrid equivalent model. Then HR, which is your reverse ratio, and HO, your output conductance, can be removed. And this one, if we have to remove this HR and HO, can slightly affect the input impedance, output impedance, and gain. Since it is slightly affected the R parameters, then we can set your HR equivalent to 0. So therefore, HRBC is equals to 0. Your HO is in Siemens using the resistance that is 1 over HO. And it is often large enough to be ignored in comparison to a parallel load. If we have a load which is only equivalent to kilo ohms, and this HO or 1 over HO usually in mega ohms, so if we have to do the parallel of the two resistance omega or mega ohms with kilo ohms will prevail. So we can also get out HO in your circuit. So we have this one without HO and HR for a common base and for a common emitter. This is what you call your approximate hybrid equivalent model. So if we have to get the relationship between your approximate hybrid equivalent model with RA model, in your RE for a common base and for your common emitter. So therefore, RE in your common base is the same as HIB. And your alpha IE in your common base, that is the same as HFV IE. So it means alpha is equivalent to HFB. Beta RE in your common emitter is equivalent to HIE. And beta IB is equivalent to HFE IB. So therefore, beta is the same as your HFE. Then the third model is the hybrid pi model. And this type of model is used to estimate high frequency response. So in your electronics devices, we are not taking or discussing high frequency response yet. So this type of circuits will not be tackled in your amplifier circuits. This will be in your electronics design. So, but we have to also get what is the equivalent model of your transistor using an hybrid pi. So using an all-resistive hybrid pi for a common emitter configuration, we have this one. This is what is inside in your transistor. We have RB prime B, RB prime C, RB prime E, GM voltage base prime E, and RCE. So we have this current IB, we have IC, and IC prime. We have voltage base prime A and BCE. So this common emitter configuration of a hybrid pi equivalent model is also in relation with your complete hybrid model. So solving for the resistive value of your hybrid pi model, we need also the complete hybrid model. So for RB prime B, which is what you call your base spreading resistance, it is related to your H parameter, HIE. So if HIE is your input resistance, that is equivalent to the input resistance of your hybrid pi model. So the input resistance of your hybrid pi model, which is equivalent to your HIE, is equals to RB prime B plus RB prime C in parallel with your RB prime RCE. Then your RB prime E, which is equivalent to your input resistance, that is equals to your RB prime E IB. We have to solve your RB prime B using your voltage base prime E. So the voltage across RB prime E is equals to your voltage base prime E. So therefore, RB prime E is voltage base prime E over IB. And IB, we have to get the equation of IB through your IC. Remember IC, that is alpha IE. If we have your input as your emitter current, or that is equivalent to beta IB if your voltage current input is IB. So this one, in your hybrid pi, your IC is equals to GM voltage base prime E. Getting your voltage base prime E, that is equals to IC over GM. Substituting your voltage base prime E to your equation RB prime E. So therefore, we have IC over GM IB. So IC in your hybrid pi model is HFE IB. So we have HFE over GM. And GM in your RE model is 1 over RE. And in your hybrid model, RE is HIB. So therefore, RB prime E is equals to HFE HIB. Then your RB prime C or feedback resistance, it is related to H parameter HRE. HRE is a reverse transfer ratio, so that is voltage input over voltage output. So in your hybrid model, your voltage input is your voltage at the base with respect to your emitter, and your voltage output is equivalent to your BC. So in terms of your hybrid pi model, if you have to get the reverse transfer ratio, that is voltage base prime E over BCE. Then if you have to apply the voltage divider bias and at your voltage base prime E, so that is equals to RB prime E BCE over RB prime E plus RB prime C. Therefore, HRE, which is voltage base prime E over BCE, it is equals now to RB prime E over RB prime E plus RB prime C. So therefore, RB prime C is equals to RB prime E over HRE minus RB prime E. For RCE, which is the output resistance, it is related with your HOE in your hybrid model. So if you have to solve for your BCE in your hybrid model, that is equivalent to your HOE times IC, or HOE is equals to IC over BCE. At the output node equation of the hybrid pi model, we have to solve for your IC prime. That is equals to your BCE over RCE, so the current flowing at your RCE, plus your GM, voltage base prime E, then plus the current that will flow at your RB prime C going to the terminal of your RB prime B in parallel with your RB prime E. So the voltage from that terminal, from this terminal, with respect to your emitter is your voltage CE. So substituting this one to your HOE, so therefore this is now your equation of your HOE. Solving for RCE, so this is the equation of your RCE. And that's all for our hybrid or your BJT modeling.